Thermodynamics is the study of energy changes and the laws governing the conversion of heat into other forms of energy. Before we dive into this chapter, it would be good to first review some important terms. Enthalpy, represented by the letter H, is the heat content of a system at a constant pressure. The change in enthalpy, delta H, is the heat that is absorbed or released by a reaction. Entropy, which is represented by the letter S, is a measure of the disorder or randomness of a system. A reaction accompanied by a release of heat is exothermic, while one accompanied by an absorption of heat is endothermic. The first law of thermodynamics states that energy is conserved. It is never created nor destroyed. For instance, in an exothermic change, potential energy stored in chemical bonds is converted to kinetic energy. As the kinetic energy of the atoms and molecules in the system and surroundings increases, the temperature increases. We might say that the exothermic reaction is giving off heat. It is important to note the difference between the definitions of heat and temperature. Heat is the energy transferred between a system and its surroundings. Temperature is a measure of the intensity of heat, the average kinetic energy of the particles that compose a material. Reactions that are spontaneous, which are also referred to as being thermodynamically favorable, occur without any outside intervention. On the other hand, non-spontaneous reactions can continue only as long as they receive outside assistance. Spontaneous does not mean the reaction occurs rapidly. Rust is one good example that illustrates this. The rusting of iron happens without any outside intervention and is thus a spontaneous process. This process is not instantaneous and usually happens gradually. Remember that exothermic changes are those accompanied by a release of energy. Exothermic changes lower the potential energy of a system and tend to occur spontaneously. However, endothermic changes can also be spontaneous, like the melting of ice and the vaporization of water. Why is this the case? An unfavorable energy change can be overcome if there is an increase in randomness or disorder. The second law of thermodynamics states that the entropy of the universe increases with every spontaneous process. Ludwig Boltzmann was a famous Austrian physicist who determined the probability that a group of particles might occupy a particular set of positions in space at any particular time. These sets of positions are known as microstates. In the Boltzmann equation, it can be seen that entropy is equal to Boltzmann's constant times the natural log of the microstates. Just quickly here, we can see that Boltzmann's constant is obtained by dividing the gas constant by Avogadro's number. In a pure crystal at absolute zero, the particles orient themselves in only one possible microstate. This means in the Boltzmann equation we are taking the natural log of 1, which is equal to 0. This means that the entropy must also be 0. Therefore, the third law of thermodynamics states that the entropy of a pure crystal at absolute zero is 0. Entropy increases as the number of electrons in an element increases. More electrons means that there are more possible microstates. When we are talking about the randomness or disorder in a system, there are two different kinds of disorder we refer to. Potential disorder depends on the arrangement of particles in space. Thermal disorder depends on how the total energy is distributed among all the particles. The more random the distribution of particles in space, the higher the entropy. The same can be said the more energy is distributed randomly. As heat is added to a system, there is an increase in disorder and therefore entropy. This is more significant when we add heat to a system at a lower temperature where little disorder exists. As seen in the equation below, the entropy change is inversely proportional to the temperature at which we add heat. Also, entropy has units of energy divided by temperature, joules per Kelvin. These could also be joules per mole Kelvin if we are calculating the entropy for a particular quantity. Note that for an entropy change of the surroundings, we place a negative sign in front of the enthalpy value. To practice applying our understanding of entropy, let's look at some examples. For these questions, I'll introduce the choices and then give you a few seconds to decide which has the greater entropy. You will also want to be able to explain why your answer is correct. Which has greater entropy, an atom of helium or a molecule of carbon dioxide? Well, both of these are gases, so we can't use the states to come up with a conclusion about entropy. Helium is only one atom, while the carbon dioxide molecule contains 3 atoms. Therefore, the carbon dioxide molecule has greater entropy. When this is less clear, we may want to look at the number of electrons for each species. In this case, helium has 2 electrons, while carbon dioxide has a total of 22. Carbon dioxide has a larger electron cloud, meaning it has more microstates and thus a higher entropy. Do 2 molecules of ozone have a higher entropy or 3 molecules of oxygen? Both molecules are in their gaseous state. A higher number of molecules means there are more microstates. This means the 3 oxygen molecules have a higher entropy than the 2 ozone molecules. Here is water as a liquid and the same amount as a solid. Which has the higher entropy? Gas particles have more microstates than liquids, which in turn have more microstates than solids. Therefore, the liquid water has a greater entropy. Let's do an entropy calculation as practice. Chloroform has a boiling point of 61.7 degrees Celsius. The enthalpy of vaporization is 31.4 kilojoules per mole. What is the entropy of vaporization? We have to be very careful with the sign of the enthalpy change. In this case, we are dealing with the system, the chloroform, and to be vaporized, it is absorbing energy. In other words, this is an endothermic change, and the change in enthalpy for the system is positive. We can then divide this by the temperature at the boiling point, but we also need to be careful here. The temperature we are given is in Celsius, but we need to convert the temperature to Kelvin to use it in the equation. Plugging this in gives us an entropy of vaporization value of positive 93.8 kilojoules per mole Kelvin. A positive sign makes sense because the entropy of the chloroform has increased. The particles have gone from a liquid to gas state, and gas particles have more microstates than liquid particles. It's always a good idea to quickly make sure that your answer makes sense once you do a problem. How about we also calculate the entropy change for the surroundings? The temperature is the same, but the sign for the change in enthalpy is different. The surroundings are losing enthalpy as they give it off to the chloroform. This results in a negative value for the change in entropy of the surroundings. The standard entropy is the entropy of 1 mole of a substance at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. The naught symbol to the right of the S shows that the entropy is at these conditions. We can find these values in tables of standard entropies. The standard entropy values of pure elements in their standard states are not equal to 0 as they are measured at 25 degrees Celsius and not 0 Kelvin. Entropy is a state function, meaning it is not pathway dependent. This means we can use the same kind of method as Hess's law calculations to determine the entropy change for a chemical reaction. Additionally, entropy is an extensive property, so we need to take into account the number of moles of all species in the reaction. To get the enthalpy change of a reaction, we subtract the standard enthalpies of the reactants from the standard enthalpies of the products. A spontaneous change in entropy is positive and a non-spontaneous change is negative. Now we can try an entropy calculation using this method. What is the standard entropy change for this reaction when 1 mole of urea reacts with water? Is the process spontaneous? Well, in this case we are given the standard entropies of all the substances, so we don't need to go look them up in a table. We then plug these into our equation, taking care to multiply each entropy value by the moles of the corresponding substance from the chemical reaction. The standard entropies of the reactants are subtracted from the standard entropies of the products. We then get an answer in units of joules per mole of reaction Kelvin. A positive value for the change in entropy makes sense because looking at the equation, the number of microstates has increased. We went from a mole of an aqueous substance and a mole of a liquid to 3 moles of gas. A positive entropy change, or delta S, indicates that the reaction is spontaneous. From what we have seen so far, it seems that whether or not a chemical process is thermodynamically favorable is determined by 2 factors, enthalpy and entropy. These 2 forces can work together. For instance, when a stone wall crumbles, the enthalpy decreases and its entropy increases, both of which favor a spontaneous change. Yet when ice melts, the effects of enthalpy and entropy are in opposition. That is, the entropy favors spontaneity in the forward direction and the enthalpy favors the reverse, which sort of makes the spontaneity of the overall reaction harder to determine. However, we can use another thermodynamic quantity called Gibbs free energy to determine the net effect of enthalpy and entropy. The equation showing the relation between Gibbs free energy, enthalpy, and entropy is shown here. A change is only spontaneous if it is accompanied by a decrease in free energy. In other words, delta G must be negative. When delta H and delta S have the same sign and are thus in opposition, temperature becomes quite important. This chart summarizes the different scenarios that result from the combination of delta H and delta S. The equation is also shown above to help us understand the effects of the different signs of delta H and delta S, as well as temperature. When delta H is negative and delta S is positive, then delta G is negative, and the reaction is always spontaneous. the temperature does not matter. When delta H is positive and delta S is negative, delta G is always positive. The forward reaction is non-spontaneous at all temperatures. When both delta H and delta S are negative, it is the enthalpy that drives the spontaneous change. The reaction will be spontaneous and G will be negative at low temperatures. As the temperature is raised, the reaction will become non-spontaneous. On the other hand, when both factors are positive, it is entropy that drives the spontaneous change. If the temperature is high, then delta G is negative and the reaction is spontaneous. As the temperature is lowered, the reaction eventually becomes non-spontaneous. Exergonic reactions are those that occur with a decrease in free energy. One example is catabolic processes, which break down proteins and lipids and result in a large number of bond formations. Endergonic reactions are those that occur with an increase in free energy. For instance, anabolic processes form biological macromolecules following a multitude of bond breakages. When one reaction is powered by another, the reactions are said to be coupled. Essentially, anabolic processes are powered by catabolic processes during the metabolic processes that occur in our bodies. Useful work is performed by spontaneous chemical reactions. Delta G is the maximum amount of energy we can harness from a reaction as work. This is the energy that is not lost as heat and is thus free to be used for work. When delta G equals 0, the reaction is at equilibrium. During a state change, the system is in equilibrium and delta G is 0. The equation below is the one we used for calculating the entropy during state changes earlier. If we know delta H and delta S, we can solve for the temperature at which equilibrium will occur. At what temperature will liquid bromine be in equilibrium with gaseous bromine? We are given the delta H and delta S values. Delta H is positive as this is an endothermic change. By substituting these values into our equation, we get our temperature. This temperature is in Kelvin, but it's generally good to have our final answer in Celsius, so we convert it over. This temperature represents the boiling point of bromine. Bromine is a liquid at room temperature, so a boiling point that is higher than 25 degrees Celsius makes sense for our answer. As our calculations are all restricted to the conditions of 1 atmosphere and 25 degrees Celsius, the Gibbs-Helmholtz equation, named after American Josiah Gibbs and German Hermann von Helmholtz, who independently derived the equation around the same time, will be used in this form. As enthalpy and entropy are state functions, Gibbs free energy is also a state function, and we can use the Hess's law method of calculating standard free energies. Note that the standard free energy of formation for an element in its normal state at 25 degrees Celsius and 1 atmosphere is equal to 0. Now let's try doing a calculation using the Gibbs-Helmholtz equation. We are solving for the delta G naught value of the dissolution of sodium chloride. We also want to determine if this is a spontaneous process. Before we use the Gibbs-Helmholtz equation, we need the delta H and delta S values for the reaction. In this case, they are not given to us. However, we can get the standard enthalpy of formation values and standard entropy values off of our tables and use them to calculate the overall changes in enthalpy and entropy for the reaction. To get the change in enthalpy, we subtract the enthalpies of formation of the reactants from the products. We multiply them by the moles of the species in the chemical equation. This gives us a value of positive 3.87 kilojoules per mole of reaction. We do a similar kind of calculation to get the change in entropy. This is just like the calculations we were doing earlier. We get positive 0.04337 kilojoules per mole of reaction Kelvin. Note that we put the entropy values in kilojoules rather than joules. Usually in tables, entropy is in joules, but when we use entropy in calculations with enthalpy, we want them to have the same energy units. If enthalpy is in kilojoules per mole and entropy is in joules per mole Kelvin, and we try to do a calculation with them together, our answer will be incorrect. Since our enthalpy we just calculated was in kilojoules per mole of reaction, we want our entropy to be in units of kilojoules per mole of reaction Kelvin. These values can now be put into the Gibbs-Helmholtz equation. If we aren't given a specific temperature for a question requiring this equation, then we can assume the reaction is at SATP conditions. That is, the temperature is 25 degrees Celsius. Still, recognize that the presence of the naught symbol does not restrict all calculations to a temperature of 25 degrees Celsius. The delta G value we get for our answer is negative, so the reaction is spontaneous. What if we use the state function algorithm method for calculating the delta G value? We get the free energies of formation values from a table if they're not given in the question. After plugging these into the equation, we end up with a value that is very close to the one we just calculated using the Gibbs-Helmholtz equation. The differences may be accounted for by the rounding we did using the state function algorithm to calculate delta H and delta S. Out of all the thermodynamic functions, delta G naught is the most temperature dependent. Delta H naught is essentially temperature independent, and delta S naught is most dependent on temperature near 0 Kelvin. Variations in delta S naught are negligible near room temperature. To calculate delta G naught at non-standard temperatures, we can still take the values of delta H naught and delta S naught from the tables and use the appropriate value for temperature. We can go back to our sodium chloride example to try out a calculation that is not at 25 degrees Celsius. For example, what is delta G naught at negative 200 degrees Celsius? We need to convert the temperature to Kelvin before we put it in the equation. In this case, the free energy value we get is positive, so the reaction is non-spontaneous at this temperature. This is consistent with the table we looked at earlier, comparing the different scenarios when we change the signs of delta H and delta S. A delta H value and delta S value that are both positive indicate the reaction changes from non-spontaneous to spontaneous as the temperature increases. As the temperature increases, a Kelvin temperature is reached at which thermodynamic favorability changes from non-spontaneous to spontaneous. This example illustrates how lowering the temperature of a reaction with a positive delta H and delta S will eventually result in a change from spontaneous to non-spontaneous. If we rearrange the equation free energy equals enthalpy minus the temperature times entropy, we get something in the same form as a y equals mx plus b equation. A plot of free energy versus temperature will yield a straight line where enthalpy is the y-intercept and negative entropy is the slope. When we try graphing this for solids, liquids, and gases, our graphs end up looking something like this. Free energy decreases as the temperature increases because all chemical species have positive values for entropy. Gases have far greater entropy than liquids and are also more sensitive to changes in temperature. Likewise, liquids have greater entropy than solids and are more temperature sensitive than solids. There are more ways for gas molecules to arrange themselves in a larger volume. Entropy depends on volume, so it must also depend on pressure. But how does the change in free energy depend on pressure? We can look at the example of the combustion of methane to derive an equation that illustrates this relationship. For the change in free energy of the overall reaction, we can subtract the free energies of the reactants from the products. If the equation shown below, which can be determined experimentally where P is some pressure, is substituted into our equation, we then get this. By collecting all the ln P terms on the far right, the log rules can be used to end up with this. The log of one number plus the log of another number is equal to the log of the product of those two numbers. The log of one number minus the log of another number is equal to the log of the quotient obtained by dividing the first number by the second. It can now be seen that the change in free energy of a reaction is equal to delta G naught plus the gas constant times the temperature times the natural log of the reaction quotient Q. The sign of delta G allows you to predict which direction the reaction will proceed. If the sign is negative, then it will proceed spontaneously forward, and if it is positive, it will proceed spontaneously in the reverse direction to reach equilibrium. While you don't need to be able to derive this equation, it's always good for our understanding of the concepts we are working with and towards developing our problem-solving skills. It's better to have some kind of understanding of where these equations come from and actually think about them, rather than simply memorizing a list of equations. Let's take a quick look at the gas constant. We are using it to get free energy, so we want it to contain units of energy, either joules or kilojoules. We can take the constant R, that is in liter atmospheres per mole Kelvin, and multiply it by a conversion factor to put liter atmospheres in terms of joules. There are 101.3 joules per liter atmosphere, so we get a value for R that is 8.314 joules per mole Kelvin. Since we usually end up working in kilojoules, we can multiply this value by 1 kilojoule per 1000 joules to get it in units of kilojoules per mole Kelvin. A mixture contains nitrogen dioxide with a partial pressure of 0.10 atmospheres and dinitrogen tetroxide with a partial pressure of 0.20 atmospheres. Use delta G to determine whether the gas mixture is at equilibrium. If not, which way will the reaction proceed? The question is asking for delta G and not delta G naught, so we know we will be using our equation we just derived here. First, the reaction quotient Q must be determined by placing the partial pressure of the product over the partial pressure of the reactant. The pressure of each species is raised to the power of its coefficient from the balanced chemical equation. This gives us a value of 20, which should have 2 sig figs. Additionally, we need to convert the temperature to Kelvin to use it in the equation. These values are then plugged into our equation. Since the free energy value has units of kilojoules per mole, the gas constant must also be in terms of kilojoules and not joules. Our answer ends up being greater than 0. A non-zero value for delta G indicates that the system is not at equilibrium. Since the sign of delta G is positive, the reaction must proceed in the reverse direction to reach equilibrium. At equilibrium, there is a minimum of free energy and delta G equals 0. Q is equal to the equilibrium constant. When we put these into the equation, it becomes this. Referring to this as the Ratlink equation helps us remember both its general form and the fact that it has a negative sign, like the tail on a rat. Whenever we use this equation, we do not want to forget about that negative sign. When we calculate the change in Gibbs free energy at equilibrium, there are three possible situations. If delta G naught is negative, then ln K must be positive due to that negative sign being on the right side of the equation. For ln K to be positive, K must be greater than 1. The reaction in this case proceeds spontaneously in the forward direction. If delta G naught is equal to 0, then ln K must be equal to 0. For this to be the case, K must be 1. In this case, the reaction is at equilibrium. When delta G naught is positive, then ln K must be negative. Thus, K needs to be less than 1. The reverse reaction is spontaneous. Two more cases we can look at are if delta G naught is very small or very big. If it is very negative, then K is very big and the reaction is spontaneous to near completion. If delta G naught is very large, then K is nearly 0 and the reverse reaction is spontaneous to near completion. The equilibrium constant K for this reaction is 24.0 at 250 degrees Celsius. What is delta G naught? Is the reaction spontaneous in the forward or reverse direction? The temperature needs to be converted from Celsius to Kelvin so it can be used in the equation. We can then plug in the values of R, temperature, and the equilibrium constant into the equation. The value we get, which is in terms of joules, is quite large, so we may want to convert it to kilojoules per mole of reaction. Delta G naught is negative, so the reaction is spontaneous in the forward direction. This makes sense since the equilibrium constant that was given is greater than 1. Now let's try going from delta G to the equilibrium constant. As in the previous example, we make sure the temperature is in Kelvin. We need to isolate the equilibrium constant in the equation. To do this, isolate ln K on the left and take e to the power of both sides. E to the power of ln K is simply equal to K. The known values can be plugged into the equation to determine the value of K. Here is where it is very important to remember that the negative sign is present in the equation. The correct value, the one we get from remembering to include the negative sign, is 1.7 times 10 to the negative 3 for K. If we forgot about the negative sign, we would get an answer of about 580, which is incorrect. Also note that we used the log sig fig rules in the calculation of our answer. Because the exponent has 2 decimal places, our answer must have 2 sig figs. As the value for K is less than 1, the reactants are favored in this reaction. This is consistent with the fact that delta G naught is positive. In an exergonic reaction, the products have less free energy and are thus more stable than the reactants. The difference between the free energy of the product and the free energy of the reactants, 2 minus 1, is equal to delta G naught. Any points between points 2 and 1 are various mixtures of products and reactants. The difference between point 1 or point 2 and any point on the curve is equal to delta G. At the minimum on the curve, the mixture of reactants and products has the lowest amount of free energy and is the most stable. This is the equilibrium mixture. The direction to reach equilibrium will always be in the direction that is downhill on a free energy diagram. In an endergonic reaction, the products have more free energy than the reactants. Therefore, K is less than 1 and the reaction is reactant favored. More reactants are present in the equilibrium mixture than products.